Hello, welcome to today's session about logical change records, LCR in short, which is logical form of WAL, write ahead log. In today's presentation, we'll talk about logical replication. We'll introduce it briefly. Then we'll talk about the technology that we are developing in BDR in order to improve performance of logical replication. There are two components to this technology. One is WAL decoder process and the other is LCR. We will talk about what's the difference between LCR and WAL, and then we will see benchmarking results. And at the end, we will talk about the insights that we got from developing this feature and also the next improvements that we are planning for this feature. Logical replication is now supported for at least last few releases of PostgreSQL. So let's talk about it briefly. So as shown in the diagram, there are two PostgreSQL servers. One, we are replicating the changes that are happening on upstream or origin to the target or downstream. So on upstream, there are regular backends which are changing the database. And while they are changing the database, they produce stream of WAL or write ahead log records. This stream of WAL record is basically each of these records tells what changed in that database in the database at the physical level. A WAL sender, which is sending the changes to the downstream logically, basically reads this WAL or this WAL record stream and then converts those into stream of logical changes grouped by transactions. The logical receiver on downstream receives these logical changes and applies them to the database and database on the downstream. And when it is applying, it also produces a stream of WAL records. As you might observe that the stream of WAL records on downstream is different from the stream of WAL records on the upstream, not just in their order, but also their content. And that is because though the logical changes are applied as they are logically, the underlying physical changes may differ between upstream and downstream, and that results in different WAL streams. Not only that, on the downstream, there can be regular backends which are making further changes to the database. So these two can act as multi-master. Both of these together can act as a multi-master application solution. But let's drill down more into what the WAL sender is doing. So a logical WAL sender has essentially four components. One is WAL reader, which is reading the WAL stream as it is produced. It feeds that WAL stream to reorder buffer, which segregates the WAL by their transaction and also orders them according to their commit order. For example, here you will see that the WAL records belong to three transactions: purple, green, and orange. And reorder buffer has segregated those WAL records And as you might notice, the pulper transaction finished earlier. So those records are ordered before green and before yellow. The third component here is the logical decoder, which reads the reordered wall as and when a transaction commits, and then it interprets this wall and produces logical change record. In order to do that, it maintains the snapshot of the database as it was when that particular wall record was applied. So using that snapshot, it interprets the wall and then produces the logical change record and sends it downstream, which is the last and fourth part of it. As you might guess, that this process of reordering requires memory. So these wall records are maintained in memory. If the memory gets full, then these records overflow to the disk. And also logical decoder has to access and maintain the snapshot. So the process of reordering and logical decoding is compute as well as disk IO heavy. So now consider the scenario when there are multiple downstreams. For each such downstream, there is a wall sender on one wall sender on upstream. So if there are n downstream servers, then there are n wall senders running on the upstream node. And each of these wall senders is doing all of this. It's reading wall record, reordering, decoding, and then sending it downstream. In most of the cases, a given wall record maps to a given logical change record. So almost every wall sender is doing the same computation of converting a wall to LCR. Thus, all of these walls, the logical decoding is the work of logical decoding is duplicated across all the wall senders. And since this is CPU and memory and IO intensive operation, when there are many wall senders, the system is unnecessarily loaded. So in order to reduce this load and reduce the amount of duplicate work that is being done, we have developed a technology which has two components, a wall decoder process and the LCR. So LCR is logical change record, which is basically nothing but the logically interpreted wall. But we have formalized what an LCR looks like, just like there is formalization of what a wall looks like. And using these two, we are able to improve performance of logical replication and by deduplicating the logical decoding work. So here is how wall decoder looks like, and it is very similar to the wall sender, except that instead of sending the logical changes to another PostgreSQL server, they are being written to the disk on the local server itself. So wall decoder again reads the wall stream, reorders it, then interprets that stream based on historical snapshot that it maintains, and then produces LCRs which are written to the disk. So in a system where we have wall decoder enabled, the logical replication architecture looks slightly different. You will see that there is an extra component here, WAL decoder, which is reading WAL and writing LCRs. And now WAL sender actually becomes a very thin process that it just reads LCR and sends it downstream. So if there are many downstream nodes, there are so many WAL senders, obviously on upstream, but all of these WAL senders are reading from the same stream of LCRs and sending it to the downstream nodes, thus reducing load on CPU and also on the disk. So what's the difference between WAL and LCR, as it is probably apparent by now? WAL is write ahead log, which basically describes a physical change. For example, which file that change happened, which block, in that block, what offset and what bytes changed. Whereas a logical change talks about the logical, basically logical view of the same WAL. It tells which table was changed, which row in the table was changed, which column, and which transaction did that change. Write ahead log theoretically does not know about transaction. They are just stream of WAL one after the other. It's the commit records which really define or rather I would say the WAL by itself need not know about the transactions. They are applied just physically to the disk, whereas LCRs are transaction aware and they need to be applied within the same transaction on the downstream. WALs, when we are replicating using WAL, a process similar to recovery is running on the downstream node, which is basically applying the WAL one by one to the physical disk or the physical view of the database, and maintaining the physical view of the database consistent with the upstream. Whereas LCRs applied logically, and they maintain the logical view of the database, not necessarily the physical view of the database. WAL, for example, includes changes to the table and also index and anything that happens to the disk, whereas the logical changes just maintain the changes to the table, not necessarily to the metadata that was changed by during when that logical change was applied. So we will see that in a way LCRs are smaller version of WAL, and they also takes lesser size, but we'll talk about that a bit later. So let's come to the interesting part of benchmarks. So we envision that this technology would improve CPU usage because now we are deduplicating the work in WAL sender. It will improve replication lag and also transaction throughput. So let's discuss these one by one. I must note that some of these benchmarks were run by Bharat Telange, who is my colleague in Enterprise DB. So thanks him for all his efforts. So let's start with CPU usage. This is the experimental setup. As I've said that this technology is being developed for BDR. So we used a BDR cluster with 9 nodes, where the PG bench was run on one of the nodes, and those changes were replicated to all the other 8 nodes. And we measured the CPU usage on the node where the load was running. This technology was originally meant to support hundreds of wall senders. So in order to test hundreds of wall senders, we introduce additional wall senders using PG receive wall. So in the next experiments, when we see more than 8 wall senders, the extra wall senders are nothing but the PG receive logical connections. So as you will see that the dark columns or dark bars are CPU usage when decoding worker is enabled, whereas the light bars or light columns are CPU usage when decoding worker is enabled. So dark bar, CPU usage without decoding worker, and light bars with decoding worker and wall senders using LCRs. We ran experiment with 3 setups, 8 wall senders, 88 wall senders, and 152 wall senders. And with each of these, we ran a different TPS. So with 8 wall senders, we ran with 1800 TPS. With 88 wall senders, 600, and with 152 wall senders, we ran TPS of 200. This combination of wall senders and TPS is slightly arbitrary, and it was meant to not overload the system when the number of overload the system and keep the measurement stable and reliable. And in all the cases, as you will notice, that the CPU used when decoding worker was enabled is significantly lesser than when decoding worker was not used. And as the number of wall senders increases, this CPU usage, or rather saving in CPU usage, also increases. On the right side, you will see graph of wall sender CPU usage. And again, as you will see that when decoding worker was enabled, the wall sender took lesser amount of, each of these wall senders took less CPU, as they were not performing any logical decoding. And the CPU that was saved in each of the wall sender compensated for the CPU that was used by wall decoder, with a net of reduction in CPU usage. In this slide, SDW really means separate decoding worker, which is the internal name that we are using for this technology. The second measurement we did was replication lag. So with logical replication, as we increase the number of transactions, as the transaction throughput increases, more wall is generated, and then a single wall sender is not able to cope up with that increased rate of wall. That causes a built-in replication lag. And as the number of wall senders increases, this replication lag in individual wall senders also increases. The reasons for that are, again, logical decoding is time and resource consuming. So, and every wall sender is doing that. And second thing is, when wall sender is busy doing IO, it is not decoding. It's not performing any logical decoding, and yet the wall is being generated. So that adds to the accumulation of wall over the time. With wall decoder, we are able to mitigate both of these conditions, because when wall sender is performing IO, wall decoder still continues to decode the transactions, except when it's actually performing the disk IO, which is not, which does not take as much time as performing network IO. And also, because of logical decoder, the time CPU and memory use resources are saved, as we have seen already. So this improves replication lag. We measured replication lag typically with a BDR cluster with 2 nodes and a resource-rich AWS instance with more CPUs, more RAM, more and faster storage, but also with higher number of parallel connections of PG bench, higher scale, and a higher transaction rate. So here's the result. As you will see that the brown line indicates the replication lag that has built over the time in wall sender, which is not using decoder, whereas the yellow line or orange line indicates the replication lag that builds up over the time when wall sender is using LCRs, and the blue line indicates the same for the wall decoder. And as you will see that there is, so the y-axis is actually replication lag in GB, and you will see some improvement in the replication lag. The rate of accumulation of replication lag is slower in wall decoder and wall sender is using LCR. And also you will see that the wall sender is keeping up with wall decoder since it's just reading and sending those LCRs. So if we can improve now this gives us a hint that if we can improve the rate of wall decoding rate of logical decoding, then automatically the replication lag itself will come down, because wall sender will anyway be able to keep up with the wall decoder. And we'll talk about it somewhat at the end. So the second, so the technology improved CPU usage, and it also improved replication lag. We expected that it will improve throughput as well, in the sense that because the CPU is saved now, we will be able to see more TPS when wall decoder is enabled. Again, this is the same setup as the CPU usage benchmarking. And we did actually see that when we are using decoding worker, the transaction throughput improves as compared to when we are not using decoding worker, except that with BDR, we are not yet able to get stable readings of benchmarking. The reason is replication interacts with the transaction throughput when we are utilizing 100% of CPU. And so the replication competes with transaction throughput, and sometimes so the transaction throughput is not stable. Second thing is also that the CPU that is saved using wall decoder does not always get used for increasing TPS. It sometimes is used by wall senders to keep up with the replication lag. So we are still looking into stabilizing these benchmarking results. But yeah, we have seen some improvement in the transaction throughput as well. Okay, I would have normally taken the questions and answers during the presentation itself, but since this is an offline presentation, I will take those at the end, and that is after we have discussed some insights and also the future of this technology. There are quite interesting things that we learned when we were benchmarking with WAL decoder. The first surprising discovery was waking up a process is expensive for the if process A is waking up process B, then A incurs a significant cost when it tries to wake up B. So in case of logical replication or general replication, when WAL is flushed, the process which flushes the WAL also wakes up the WAL senders. And if there is a high number of WAL senders, then the process which does the WAL flush and wakes up WAL senders incurs a cost in waking up those WAL senders, which causes a transaction latency. I mean that the transaction latency in such cases increases. So with WAL decoder, the transaction latency comes down because now that process does not need to wake up the WAL senders. The process which is doing WAL flush does not need to wake up WAL senders, but it has to wake up only WAL decoder. But now that cost of waking up WAL senders is incurred by WAL decoder, and it slows down the WAL decoding process. And interestingly, the load of flushing WAL is distributed across the backends, or there is a dedicated process which does buffer cleanup or background writing, which also does WAL flushes. So that cost, the cost of waking a process, is not usually visible, whereas when that is incurred by a single process always, it considerably slows down replication, and also it is visible in terms of the replication lag. The second discovery was that the file read and file write APIs that PostgreSQL provides are affected by interrupts. So when, let's say, a WAL sender is reading LCR or even WAL, or WAL decoder is reading WAL or LCRs, if an interrupt occurs, if somebody else tries to wake it up, then the file read or file write operation is interpreted and it is repeated, causing higher CPU consumption and also IO. So in order to mitigate this, we introduce buffered read and writes, where the WAL decoder accumulates LCRs before writing them to the disk, and WAL sender also reads bunch of LCRs, at least one transaction worth LCRs at a time from the disk. So as to improve, so as to mitigate this problem. Nothing new, but it at least again reaffirms importance of buffering for disk IO. And third is the WAL sender support in the core PostgreSQL itself. As we have already seen that the WAL sender and WAL decoder, they are very similar, except that the WAL decoder writes to the disk, whereas WAL sender sends it to the other PostgreSQL server. But WAL sender.c, which is the C module implementing WAL sender, is heavily tied with a socket client. So it expects that that the process in which that module is running has an open socket through which it is sending these logical changes. And for WAL decoder that is not true. So we could not use WAL sender module as it is. We had to duplicate that code and make WAL decoder look as a separate process. Which means that the WAL decoder could not take advantage of some of the privileges available to WAL sender process. For example, there is WAL send wake up cycle, which the WAL flush uses, or shutdown cycles gives higher chance or more time for WAL sender to shut down, so that it has some time to send all the available WAL downstream. But both of these privileges could not be extended to WAL decoder, and so we had to introduce a hook which could replace the WAL send wake up cycle, and we don't yet have a good solution for shutdown handling. So if we could get this feature, so if we could architect the WAL sender in such a way that the socket is not required always, then it will help a lot to the WAL decoder, and it also will improve the performance of WAL decoder. So, okay, let's come to the end of this presentation and talk about what we are planning next for this technology. The first in the line is parallel decoding, and as we have seen in an earlier slide, that although the replication lag is lesser when we are using WAL decoder, we are still seeing some replication lag. And in order to improve that situation and support logical replication in systems with very high load and higher number of WAL senders, we will bring parallelism to logical decoding, where we can add multiple processes or multiple backends which can perform logical decoding in parallel and thus improve the throughput of logical decoding. This is not practical with the regular WAL senders, since each of those WAL senders which is doing logical decoding will also require these logical processes, which means that the number of parallel backends we will use for WAL senders will increase with the number of WAL senders, and we might end up using tens or hundreds of workers just for replication. Whereas with the decoding worker, we can manage to keep up with the logical decoding just with a few handful parallel workers. The second improvement is logical backup. Now that we have formalized the notions of LCR, what LCR can contain, and we are also seeing that LCRs consume lesser space because many of the things that are in WAL are not there in LCR. We are building systems so that LCRs can replace WAL, either for logical backup or also to improve the wall retention. So when when a when a downstream to which we are replicating changes logically goes down, we need to retain the wall on upstream, and also we cannot forward the catalog xmin because we need to interpret the wall in logical way. With LCRs, since we have already converted the wall to LCR, we don't need to hold the xmin back, and also we don't need to retain wall. We can produce LCRs, archive them somewhere, and and take the load off of upstream. When the downstream comes up, we can apply those LCRs which have been saved somewhere to the replica and then bring it back and see in sync with the upstream. So that I think will change. That we think will change the face of logical replication in and improve. I mean, overcome the problems that are being faced with the logical replication today. With that, I end my presentation. Thank you. And we will open for question and answers.